So this is the list of a few applications that my team and I have worked on that have been specifically blocked by fragmented shielding. In gaming, you can't have protocols with buried treasure and deceptive alliances. In finance, you can't have dark pool suites and RFQ insurance. In social, it's blocking pre-release content, community-specific feeds, and more. There's a rich design space here that we have yet to dig into for the most part as a community. And this is because of shielded fragmentation. And the fix of this is making the fragmented state interactive. And this can be thought of at a high level as making it multiplayer, whereas there's an informal definition here. We have each person, we have n equals 3 here. We keep state off-chain, and then keep a commitment to the state on-chain. Then we introduce an agent G, who needs to compute updated state commitments for each of the users that are publicly verifiable without revealing anything about the intro commitments and then the out commitments. And then we note that G may or may not be in the original set of 3 participants. And so for a PROGCRYPTO audience in particular, this definition likely looks really familiar to you because it's MPC. And you're absolutely correct. It's MPC with the following changes. Number 1, we want the interaction to be verifiable for external users, not just the people participating in the protocol. Number 2, we introduce an agent G that can do the full computation. And then number 3, we also want shielding to be permeable. The way that we define permeable is that people within the same groups of these in these protocols can learn a little bit about each other's shielded state. And these 3 changes make MPC completely different in our context. So classical MPC constructions can't do what we need it to do here. Moreover, classical pure constructions in zero knowledge and fully homomorphic encryption also similarly cannot. There are many reasons why this is the case. I won't go over them, but for the most part, it's the same principle as with here. We have 3 requirements that look like they've been chosen randomly, and we have 3 methods, ZK, FHE, and MPC, that I just say you can't do things with. We don't have time to go into them in detail, but as an exercise, if you're curious, you can try implementing any of the protocols that we listed on this slide, and then you'll, it's many slides before, and then you'll eventually run into this problem of fragmented shielded state, and you'll need the 3 requirements, and you'll realize you can't do it with pure constructions on each of these pillars of cryptography. And so what do? We mix and match. We have the 3 pillars, we take little bits from each of the technique verticals, and then we stitch them together into an end-to-end system that fulfills all of our requirements for interactive shielding while having a security model that we're satisfied with. And one of the points that we always drill in our constructions is it's always simple cryptography. We're a group that's specifically focused on shipping applications on the timeline of months. So we care a lot about not having complex constructions that take large teams of mathematicians to implement and then larger teams to audit. So simple cryptography is a big one. And with that, we'll get into how we think about this. Because right now, there's a full decentralized trust-minimized construction that we can build today. Like we know how to do it using specific techniques, but it would be a mistake to ship that version today. And the reason is because the UX hit that we take on the fully trust-minimized solution is large enough such that it'll stop adoption. And at every step of the way, really the goal here is to have adoption and have the combination of application momentum, user experience, and trust such that we get adoption at every step. And so what we're proposing we do today is we start off with the best UX. We impose stronger trust assumptions so we can deliver a great user experience. And then after that, we eventually relax these trust assumptions over time, which degrades the user experience. But eventually, once we get to the last phase, we're taking a phased approach here. Once we get to the last phase, we're in the fully trust-minimized world while having enough momentum with the transformative applications that we build such that people are willing to stick it out even over the UX hurdles. And so I'll be talking about our phase 1 construction today in particular. And in this construction example, we have Alice and Bob. These are 2 parties who want to participate in a protocol whose shielded state needs to interact. And we have the chain as the source of truth. And they do this using this sequence. We introduce a set of providers. These providers are tasked with sharing knowledge between party A and party B. If you remember in our example earlier, whenever we have shielded state, we have a commitment on-chain, we start somewhere off-chain. If this is stored on user devices, then users are responsible with interacting with the protocol. If we store it with providers, then providers can be responsible with interacting with the protocol, which incurs a trust assumption but has a great UX. And so we have providers that we call shielding providers. And as I said, whenever someone moves, they share the pre-image to their commitment with the provider. After that, they actually move. This bottom one doesn't actually do anything for them. It's more of a knowledge-sharing procedure. And on the top, they can actually do their move by submitting a ZKP that their new commitment abides by the validity predicates of the protocol. And then that's them actually moving on-chain. After this, the providers you get a transaction confirmation from the chain, because again, the chain is the source of truth, including for the providers, that Alice actually moved. And then after this, we have something that we call interaction predicates on what is the conditional that allows two people's shielded state to permeate. And if those predicates are fulfilled, then the providers tell both Alice and Bob that, hey, your guys' state intersect a little bit. Here's a bit of information about each other's state. And then finally, we have, remember we introduced the agent G earlier? We set that agent to Bob right now, and we want Bob to be able to do the full computation. And using the knowledge that the providers have given Bob, then Bob can transition the Alice's commitments and Bob's own commitments with a zero-knowledge proof. So effectively, we've hit all the requirements that we see here. You can verify everything because there's ZKPs. G can do the full computation as Bob did. And then shielding is also permeable because the pre-images are stored with the providers and not with the users themselves. And so users don't have to be online all the time to reveal parts of their state upon seeing on-chain conditions being fulfilled. And so now what we're really doing here is we're introducing a set of entities that are centralized and trusted in the system, and this is really dangerous to do. So it's a delicate process to do this in such a way that the providers are weak as possible. We introduce these entities, and we strip them of every trust assumption we can until we leave them with a base trust assumption that we must impose for the user experience. And this includes you can't do any logic on the providers. You should never do any logic on the providers because state and the provenance that is attached should always be certified via cryptographic and proof-of-stake trust assumptions. You should also have permissionless data extradition, so providers can't hold the pre-images hostage. You should also never do any ordering, so you'd never have privileged actors that enter into the MEV pipeline. And there's a long list of these. And I can't stress enough that this is a dangerous thing to do, and you must do this really carefully. It's simple cryptography, but you need to be very careful about what trust assumption you're providing through the person. And then now finally, what this gives us is that state is very much still on-chain. State transitions are very much still secured by cryptographic and POS trust assumptions. And then a copy of the state exists in shielding providers. The actual state itself does not exist in the shielding providers, and that's important. We need to do everything we can to keep it that way because there's a big difference in what happens between these two cases. And so what we've really done here is we've asked, what are the properties that people want when they build blockchain applications? We listed them all out, and we put as many of them on the left as possible, because the left is really what we want. And there are many buzzwords here on the left that are blockchain properties that are fairly untouched with having this interactive shielding construction. And there are a lot of buzzwords. What this actually means is that in the event of a full compromise, so this is a catastrophic event where the adversary gets full control over one of the providers that a protocol trusts for interactive shielding. And in this case, even though the adversary is full control, they still can't invent money, can't steal, can't hold funds hostage, and can't delete. And that's the upshot. That's what we're trying to accomplish with this construction. But of course, it's not a perfect world. We still have a provider trust assumption on shielding. If a provider is fully compromised, they can leak information about the protocol. And this is really bad. This is why most providers, we require them to run in trusted execution environments. But with the existence of side channel attacks, this is still an imperfect solution. So really, to take this bad trust assumption out, we need to do it over phases where first we relax it using, it's a network I'm not going to talk about too much, a network for threshold re-encryption, and then eventually we remove it completely using a 2PC network. So we need this to be relaxed over time, but for shipping today and creating applications today, this is a security model that we've ran by many partners, and we've found is sufficient for us and sufficient for their purposes. And so the three takeaways that I'd like to end my talk with here are, number one, interactive shielding is important. It's something that you'll start seeing a lot more of in the next few months. Two, there are 3 phases of decentralization for this, and there's a particular reason for it, because we want some combination of momentum and UX and trust that we're okay with and people have great experiences with. And then finally, I'd like to get the conversation started more in our community where we decouple the blockchain properties that we want to provide. Usually in our community, we'd say we want it all, but that's really not the way to provide a great experience and great adoption of our technology. What we really want to do is take all of the properties that we want, and then we tease out exactly what's hyper important, very important, and then important. And then with all of that, we can create these mix and match systems that stitch together different types of cryptography to fulfill all the requirements, deliver great experience, and have a security model that we like. And then finally, for some acknowledgements, we are definitely not the first to build interactive shielding. Many incredible projects have done this before us under specific trust assumptions and interaction types. So all of these projects are listed here. We've learned a lot from them, so all the credit goes to them. And then finally, I'd also like to thank all of the contributors to this project who have brought it to where it is today. We couldn't do it without them. These contributors are Dan Bonet, Wei Dai, Ying Tong Lai, Eddie Lazarin, Ayush Gupta, and Andrew Liu. And that's it for the session. Thanks so much for attending, everyone.
Nice. We have time for 1 or 2 questions, maybe. Oh. So if anyone wants to jump in. Come on. Everyone understood everything? We have 1 question there.
Yeah. What's the?
Can you use the mic? Thank you.
What's the? I guess the main essential difference between a shielded state and like a secret witness.
Oh, great question. So shielded state has a broad definition where you can either talk about shielded state as the little commitment that's existing on-chain, because that's the one that has provenance attached. So that's actually what represents the state. The preimage of the state is what goes into the secret witness. So when the construction that we saw earlier, where Bob sent the ZKP to the chain to transition both his and Alice's state, what he learned from the provider about the parts of Alice's state that he needed went into a secret witness for the ZKP. And that's exactly the relation.
Okay, so like Bob is able to take a carefully selected piece of information and sort of compose that into his secret witness.
Exactly. It's the provider selected for Bob, because Bob doesn't get all of Alice's state. That's something that's not desirable. But the provider selects some bare minimum that Bob needs to create the counterparty ZKP.